In this video, we are going to learn how to evaluate double integrals over rectangular regions. This also means we will wind up reviewing many integration techniques as well. Starting off, evaluate the integral from 0 to 3 of x plus y squared dy. So we're taking a single integral of a function of two variables. X plus y squared means we have a function of x and y. We're integrating with respect to only y. So this is referred to as partial integration. Very similar in the previous unit to partial differentiation. We're going to integrate now with respect to only one variable at a time. So integrating this with respect to y, the integral of x will give us xy, and then the integral of y squared will be 1/3 y to the third. And we're going to evaluate that from 0 to 3. Since we are integrating with respect to y, the bounds they gave us are y values. So same thing here, which means we're plugging these values in for y. That means we should be left with only x's when we are done. So here we would have 3x plus 27 times 1/3, so plus 9, and then minus 0, so we're left with 3x plus 9, which is in terms of only x. That is our first partial integration problem, where we integrated the function x plus y squared with respect to y. Now let's build upon that and have a double integral. Evaluate the double integral now of x plus y squared dy dx. So that does mean we're integrating with respect to y first, then with respect to x. And we can see that if we isolate the innermost integral with the innermost differential there, that's the integral we just completed up above, and then we're left with the integral in terms of x, and then those other bounds are x bounds now. So these are x equal. So we've already completed the inner part of that integral. So we have the integral from 0 to 2 of plus 9 dx. Integrating with respect to x, 3 over 2 x squared plus 9x. Evaluate that from 0 to 2. Again, these are x values. So we'd have 4 times 3 halves, so that's 6. And then 9 times 2 is 18. And if we input 0 for both those terms, we would get 0. So 24. So there's our first double integral. Really, it's just the process of evaluating two single integrals. And we call that process an iterative process. So we refer to these as iterated integrals. An iterated integral is of the form double integral of the function f of xy dy dx. So the inner bounds are the y bounds. The outer bounds are the x bounds then. Or if we change the order so that we integrated with respect to x first, then y, then the inner bounds become the x bounds, the outer bounds become the y bounds. And just to highlight the process we went through, we're integrating the innermost integral first and then working our way out. Same thing would happen here. Right? So if we want to make a note, we evaluate inside out. And that will be true as we progress into triple integrals, the same process. We evaluate from the inside outwards. Now, with iterated integrals comes a theorem. So we have Fubini's theorem, which states that if the function f of xy is continuous on the rectangular region R, defined over the interval a to b and c to d, remember this is our x interval, this is our y interval, then the double integral over that region R of the function f of xy dA is equivalent to the double integral of the function evaluated dy dx, which is also equivalent to the double integral of the function evaluated dx dy. So the difference of what we just defined on the previous slide and here is the equality. So this theorem says that the order that we integrate in does not change the value of the double integral. Okay, so order does not matter here. as long as our bounds match up with the differentials correctly, right? So our inner bounds should be our y bounds, outer bounds should be our x bounds in this middle double integral, and then similar, but x and y would be switched. Okay, so if everything lines up, whether you integrate with respect to y then x or x then y, we should get the same answer. And that's a really important result and one we will look to build upon. It's not always going to be as easy to switch the order of integration as it is when we're dealing with rectangular regions, and that definitely is something that we will focus on in future videos. So evaluate the double integral over the region R of xy dA on the region R defined as 1 to 2 as our x interval and 3 to 5 as our y. Okay, so again, just for emphasis, there's our x, there's our y. So essentially what Fubini's theorem says is the order that we set up this double integral in doesn't matter. So we'll create an iterated integral, x, y, and let's go dy dx. So y bounds then would go from 3 to 5. The x bounds go from 1 to 2. And now we start the process of integration, working our way from the inside out. So integrating with respect to y first, so 1 to 2, we have xy squared over 2. Evaluate that from 3 to 5 dx. And for the first few examples, it may be helpful for you to note, right, which values each bound represents, because it's important when we go to plug in. So here we're plugging in the values 5 and 3 to the y values. So integral from 1 to 2 of 25x over 2 minus 9x over 2 dx. We can simplify that. Makes integrating easier. So that's going to be 16 over 2, which is 8. So 8x dx. Integrating with respect to x, we get 4x squared. Evaluate that from 1 to 2. So we'd have 16 minus 4, which is 12. And now Fubini's theorem says that if we were to start this problem over again, but switch the order, so go dx, dy, switch the bounds accordingly, and go through that same process, we should also get 12. And that would be a great exercise for you to complete just to understand how to integrate these iterated integrals, but also what Fubini's theorem is giving us. Our next example, some practice with integration. Evaluate the double integral of the square root of 2x plus y dx dy. So the inner bounds from 0 to 2, those are our x bounds, and the outer bounds from 0 to 4, those are our y bounds. So we need to integrate with respect to x first. So I'm going to underline what's inside of the square root. That's 2x plus y. If we were doing a formal u substitution, which you could do, this would be your u. U would be equal to 2x plus y. And then du, the derivative, would be 2. So we're going to put a 2 in front, over 2, circle the 2, that would be your du term. And now we're integrating, or think about integrating, u to the 1/2. So that is going to give us the integral from 0 to 4 of 2x plus y to the 3/2 times 2/3, but also times this factor of 1/2 that we put into the problem. And we're going to evaluate from 0 to 2, and those are x values again, and then integrate with respect to y after we've evaluated. So integral from 0 to 4, so we have 1 over 3, 4 plus y to the 3/2 minus 1/3 y to the 3/2 dy. So essentially, we're still doing u substitution with this underline and circling method. We're just streamlining it so that we're not writing it separately. If you need to see it separately, do so, but make sure you get pretty efficient at that, because double integrals, you might be doing that twice within one problem. Now we're going to integrate with respect to y. So we do have an inner part here that we might want to think of as a u. So if u were to be 4 plus y, then du would be 1. So there is no adjustment necessary. which makes life a little bit easier for us. So that's really just thinking of the integral of u to the 3/2, which would be to the 5/2, u to the 5/2 times 2/5. So we have 1/3 times 2/5 times 4 plus y to the 5/2 minus 1/3 times 2/5 y to the 5/2. And we're evaluating this from 0 to 4. So we have 2 over 15. If we plug in 4, that's going to be 8 to the 5/2. And then minus 2 over 15, 4 to the 5/2. And then if we plug in 0, minus 2 over 15, 4 to the 5/2. And then plug in 0, we'll get 0. And this expression can be cleaned up. Let's see what that would look like if we cleaned it up. So it would be 2 over 15 factored out. And then that would be 2 rad 2. And then to the 5th, so you'd have 32, 128 rad 2. And then minus, so square root of 4 is 2. 2 to the 5th is 32. 32 minus 32, 64. Definitely a cleaner looking answer. I don't necessarily know how necessary that is, but it definitely looks nicer than the answer that we had over there. Next example, again, just getting more practice with these iterated integrals. Evaluate the double integral of x squared e to the 1 plus xy dy dx. So this problem, just foreshadowing a little bit, is going to incorporate another integration technique that we haven't seen yet. So if we were going to do this like a u substitution, we would underline 1 plus xy. That would be our u. Our du, if we integrate that with respect to y, would be x. So we have an x squared there, which we can say is x times x. So one of those x's gets circled as the du term, right? So u substitution does get a little bit trickier because you have multiple variables going on here. But 1 plus xy is what we would treat as u. Differentiating that with respect to y, we would have x. So we circle that, that would be our du term. So now integrating, we have the integral from 0 to 2 of x e to the 1 plus xy, evaluated from 0 to 1 dx. And just our reminder, these are y values that we are plugging in. So we have the integral from 0 to 2 of x e to the 1 plus x, and then minus x times e to the first. Right? If y was 0, e to the first dx. Okay, so far, not bad. And now we go to integrate with respect to x. We would underline 1 plus x. The derivative of that with respect to x is just 1. Well, we have this x term here. So in order to integrate this, we need to integrate by parts. Okay, so I will do that over here. So we have a u and a dv term. So we're going to let x be our u term, e to the 1 plus x be our dv term. So we can differentiate down the u column, so 1, 0. Integrate down the dv column, which is nice because all of these integrals are just going to be e to the 1 plus x. Connect them, signs. So that integral for that term is going to be x e to the 1 plus x minus e to the 1 plus x. And then integrating the xe term minus x squared over 2e. And we're evaluating that from 0 to 2. So a little bit of review with integration by parts here. Now we plug in, so we get equals to 2e to the third minus e to the third minus 2e And then if we plug in 0, we'd have 0. And we'll write it out, so minus 0, and then plus e, and then plus 0, distributing that minus to each of these terms. So then that would give us e to the third minus e. So a little different here with this iterated integral requiring integration by parts. Hey, remember selecting u and dv, I should have mentioned it earlier. That's that acronym LIPIT that we use to decide which term we should make our u. So in this case, that polynomial-like term of x comes before the exponential term. So x was our u term, e to the 1 plus x was our exponential term. Right? And that will change from problem to problem. Especially look out for logarithmic terms. There will be double integrals with logarithms in them, and that will require, or sometimes will require, integration by parts there. Evaluate the double integral of x times cosine of xy dx dy. So starting this problem off, it looks like we may fall into another integration by parts. We would underline xy, differentiate that with respect to x, we would get y, but there is no y term in front. So that would require integration by parts done this way. But this problem is here to offer a different approach. Remember, Fubini's theorem says that the order that we integrate doesn't matter. So let's pause for a second and change the order and see if that can potentially give us an easier double integral to evaluate. So if we check, so we're going to take the double integral now from 0 to pi over 3, 0 to 3 of x cosine of xy dy dx. So not only are we changing the order, we need to change the bounds here. Okay, so we're going to try to change the order. Now if we run through that same process we did, we underline xy, we differentiate that with respect to y now, which would be x, and we have an x term in front of the cosine. So now we do not need integration by parts. We can run through like that u substitution type problem we've been doing. So xy would be like our u, du would be x, which we have that term. So this is going to equal the integral from 0 to 3. We're integrating cosine of u. So that's going to be sine of u, which is xy. Evaluate that from 0 to pi over 3 dx. So integral from 0 to 3 of sine of, we're plugging in for y now, so pi over 3x, and then minus sine of 0, which is 0, so dx. Okay, now we have to integrate this with respect to x. So again, we have an inner term we want to highlight. So if we think about u being equal to pi over 3x, then du would be pi over 3. So we need a pi over 3, and we'll divide by pi over 3 as well. So that term of pi over 3 is our du. So we'll think about this as integrating sine of u. So that's going to be negative. We'll flip that, so 3 over pi, right? 1 over pi over 3, or 3 over pi. The negative is because the integral of sine is negative cosine. And then we have pi over 3x, and we're evaluating that from 0 to 3. Okay, so we have negative 3 over pi, and we'll just leave that factored out. If we plug in 3, we have cosine of pi, and then minus cosine of 0. So we have negative 3 over pi times negative 1 minus 1. So we get 6 over pi. So this is a problem that started out potentially requiring integration by parts, but luckily we were able to switch the order and really solve a much simpler double integral. And that is one thing that Fubini's theorem allows us to do. By saying that the order of integration doesn't change the value of the double integral, we're able to change the order when it is beneficial to us. Okay, so there are certain double integrals that fall into a special category. If the function f of xy is a separable function, which means that the function of two variables can be written as the product of a function in terms of one of the variables times a function in terms of another, right? So that's illustrated here. So function of two variables, f of xy, can be expressed as a product of g, which is in terms of only x, and h, which is in terms of only y. If that's true, and it's integrable over the rectangular region R, a to b, c to d, then what we are able to do is take the iterated integral and separate it. So we can separate it into two single integrals, one with respect to only x, one with respect to only y. So there are two requirements for this to work. Our bounds have to be constant. So the bounds, let me change color. Okay, the bounds need to be constants. And this fact has to be true about the function, that it can be expressed as the product of two functions. So I think this makes a little more sense when we put an actual example underneath. So evaluate the double integral of cosine of 2x times sine of y dy dx. So we have constant bounds, which is true for every problem in this video because we are integrating over rectangular regions. We'll figure out what that looks like when we don't have rectangular regions in the next video. And we have a function that is the product of two functions. This is in terms of x, right? And this is in terms of y. So separating them, so we'd have the integral from 0 to pi over 4. I'm taking the x bounds, right? Just a reminder, the outer bounds are the x bounds, the inner bounds are the y, of cosine of 2x dx times the integral from 0 to pi sine of y dy. The advantage of this is we are now integrating simultaneously as opposed to iteratively. So here we don't have to do one integral, plug in the bounds, and then do the other. We can do both integrals at the same time and then get our answer. So integrating with respect to x, so 2x would be considered RU, derivative would be 2 over 2, so we circle that 2, which would be the du term. So we have 1/2 sine of 2x, and we're evaluating that from 0 to pi over 4. And then times the integral of sine is negative cosine of y, evaluating that from 0 to pi. So we have 1/2 sine of pi over 2. I'll write that out, sine of pi over 2, minus 1/2 sine of 0. We're going to multiply that by negative cosine of pi minus a negative, so plus cosine of 0. So sine of pi over 2 is 1, so we have 1/2 minus 0, so 1/2 times cosine of pi is negative 1, so negate that, we get 1 plus 1, so times 2, so we get 1. So this is an example of a separable integral. There was an earlier example that could have also been done as a separable integral, but at the time we didn't know that that was a possibility. And that was the example on the slide with Fubini's theorem. Use a double integral to find the volume above the xy plane bounded by the surface z equals y squared times x plus 2y cubed to the fourth, and the planes x equals 0, x equals 2, y equals 0, and y equals 1. So this problem really brings together the ideas of this video and the previous, in the sense that double integrals represent volume. So setting up a double integral and evaluating it will give us the volume bounded by the surface and the xy plane. And remember, it could be signed volume. So if we were to get a negative value, that would mean that most of the volume is below the region that is defined for us. Right? And without a graph, we wouldn't know if all of the volume is above. We would have to really look at the function and make sure that it's always going to be positive, which this one will be, right? Y squared, and then that expression to the fourth, these z values will always be positive, so it will truly be volume. Okay, so setting up, we have our double integral. We're going to integrate the function defined as the surface, so y squared, x plus 2y to the third to the fourth. Fubini's theorem says the order doesn't matter, but there's a little asterisk next to that. Sometimes the function tells you it does. So before we even put dy dx or dx dy, if we highlight what we would make u, and we look at what's in front, being a y squared, it's going to be easier to differentiate that u term with respect to y, because then we can use this term in front. It is possible with respect to x, doesn't really change much, but it would be nicer to do with respect to y first, since we have that y squared term here. Okay, so order here doesn't matter, but I personally think that integrating with respect to y would be easier first. So dy dx, and it won't always be the case that either way works. This one it does, but there will be cases where one way works better than the other, or only works one way. So if we're going dy dx, so we're going 0 to 1, and then x goes 0 to 2, right? Those planes do give us our region in the xy plane. Right? If we go xy plane, the plane x equals 0, y-axis x equals 2, will look like that. We'll call that 2. Y equals 1, look like that. So there's that rectangular region we're integrating over. Okay, so let's continue that u substitution type integration we started. So the derivative with respect to y is 6y squared. So we need a 6 over 6. Circle what would be the du term. So this is going to be equal to the integral from 0 to 2 of 1/6. Imagine integrating u to the fourth would be u to the fifth over 5. So I'll multiply by 1/5. X plus 2y to the third to the fifth. Evaluate that from 0 to 1 dx. Those bounds are the y bounds. So plugging in to our y's, we get 1 over 30 x plus 2 to the fifth minus 1 over 30 x to the fifth dx. Now we integrate this one, the first term rather, with the x plus 2. Right? It might need a u substitution type problem, but du would be 1, so we're good. Okay, think about u to the fifth, integral would be u to the sixth over 6. So 1 over 30 times 1 over 6 x plus 2 to the sixth minus 1 over 30 times 1 over 6 x to the sixth, evaluated from 0 to 2. So what do we get? Let's factor out a 1 over 180. And then if we plug in 2, we get 4 to the sixth minus 2 to the sixth minus, if we plug in 0, we would also get 2 to the sixth. And then plug in 0, we'd get 0. So this is going to be equal to 1 over 180. And we can just leave it. So 4 to the sixth minus, what would that be, 2 to the seventh? Right, 2 times 2 to the sixth. And that's fine. We can leave our answer there. If we really want an accurate answer, we would need a calculator for this anyway. Right, so we would stop right there. So there's our practice with evaluating double integrals over rectangular regions. Fubini's theorem is the main concept that we need to talk about, which says the order we do the iterated integrals in does not affect the value of the double integral. And we saw it come into play in a few places. If we have to pick the order of integration, it allows us to pick either based on the function, or there was the example where switching the order actually made it easier for us to integrate. A little integration by parts as well, but really with any integration, the more practice problems you see, the better you get. So I'll see you in the next video.